Seeing that first picture from the Event Horizon Telescope of the supermassive black hole at the heart of M87 was like one of the most amazing events in astronomy in recent years. And then we saw another one from the Milky Way at the heart of the Milky Way. Two black hole event horizons. But unfortunately, that's it. That's the limit. That's as much as the Event Horizon Telescope can see without being able to go off planet and build a much larger telescope. We're kind of stuck. And not only that, but there are other features that are closer in to the black hole. There is the photon ring, where light itself is being dragged around the black hole, orbiting it as if like a satellite was orbiting a black hole. But to be able to resolve the photon ring around the black holes that we've already seen is going to require like another order of magnitude in resolution to be able to see that. And so once again, you've got to go to space. Well, my guest today is Ben Hudson. He's a spacecraft systems engineer at KISPE Space, and he's been thinking about how do we get a radio telescope that can be part of the Event Horizon Telescope collaboration, but from space, where you start to get a baseline that is big enough to give us that resolution. So we talk more practically about what it would take to be able to observe the photon ring around a black hole. What are the kinds of orbits that make sense to place a telescope like that? And what kind of actual technology would be required? Like a giant radio dish, something smaller would be similar to a bunch of Christmas trees, like the square kilometer array. What is the right solution to that? So enjoy this conversation with Ben Hudson. Ben, what is a photon ring?
So the photon ring is this region around the black hole where essentially photons that have approached the black hole, either from just the universe or from the accretion disk around the black hole, essentially get trapped in this semi-stable orbit. So they don't go close enough to the black hole to fall into it, but they do pass close enough so that they're not going to fly straight by. So essentially the photon rings are these orbits that the photon itself will complete around the black hole. And then we essentially classify the photon rings based on their order, n, and this is the number of half orbits that the photon has completed around this black hole. So a photon ring of the first order would have completed a single half orbit before getting sort of projected back out, towards the observer, towards us who's seen the photon ring. The second order photon ring would have completed a full revolution before being projected back out into the universe.
But how well does I think about orbits and I think about, say, satellites orbiting Earth, but it's light. And so it's different. And so how well does thinking about orbits of matter compare to orbits of light around a black hole?
Yeah, it's an interesting idea. And obviously, everything we do around the Earth is very much based on a very simplified understanding of gravity, like a Newtonian understanding of gravity. We don't really take into account, Einstein, general relativity, physics. But as soon as you're this close to something as massive as a black hole, the whole calculation is done based on general relativity. So it's a very different in the terms of calculation of these orbits. As you approach something as massive as a black hole, the environment around it, we cannot make any of the simplifications that we make nearer the Earth for normal matter.
And I mean, when I am, say, seeing a gravitational lens and I'm seeing the light that's being distorted by a mass that could contain a black hole, that is like the very beginning stages of what a photon ring might be, because we're seeing the light being distorted by the mass of the black hole. And then it's just increasing amounts of shift. And so for you, is it like it has to be going like halfway around the black hole before it really starts to pique your interest?
So essentially what we're seeing in the Event Horizon Telescope images, the famous images of M87 star and the supermassive black holes that the telescope has taken pictures of, is what we call the direct emission. So this is light sort of propagating directly from the material around the black hole. And for us to, when we talk about the photon rings, then yes, those are those photons that have done at least one half revolution of the black hole. And that's where we become really interested in being able to, probe those structures. As soon as they've completed at least one revolution, we're beginning to, or one half revolution, we're now talking about these photon ring structures, which have, a number of interesting properties compared to that direct emission that we see in the Event Horizon Telescope images.
And so if you were to compare, like, say you've got the actual, I mean, we always describe it as the event horizon is that part, the Schwarzschild radius, the surface of the black hole, and then you've got these different features as you move away from that point of no return. But then we're talking about the Event Horizon Telescope taking a picture of a black hole's event horizon. And now it all gets confusing again. So if you were to like start at the singularity and move outward, what are the landmarks that you would experience as you break the laws of physics and escape the black hole?
Yeah, sure. So we obviously have a singularity at the center of, we presumably have a singularity at the center of a black hole. Obviously, everything happening inside the black hole is very much up for debate. We cannot see inside of that region. Everything's very theoretical, but beyond that, within that boundary. Outside of the event horizon, we now have the photon rings. And we're going to have the higher order photon rings the closer we are. So photons that have completed more and more revolutions about the black hole before falling in. And as we move away, we get into the lower order photon rings. So n equals 3, n equals 2, n equals 1. So the first order photon rings are photons that have completed just a single half revolution quickly around the black hole. And then we're out to the accretion disk. And the accretion disk is matter that is slowly falling into the black hole. So I think we often picture black holes as these, all eating monsters that take in everything that's nearby, but it can actually be quite difficult for matter to fall into the black hole. If something is close enough to it that it only feels, a very weak gravitational force from it, or far weaker than required to physically pull it in, then it can take an awful long time for that matter to actually collapse into, beyond the event horizon. So we get this big disk of plasma. It's essentially like a plasma material, which is all of the matter that has come close to the black hole and been torn apart by the gravitational tidal effects close to the body. But this plasma is all that material getting close to the black hole. There's massive friction in there, so we have huge energy emission from that region in across a range of wavelengths, throughout the spectrum. And that is really what we're seeing in the Event Horizon Telescope images. So this is when we go back to this idea of taking a picture of the shadow of the black hole. So that hole in the middle of the famous orange photo around the black center, and that really is the emission from this accretion disk. So that's how we can find it. We're almost taking pictures of the black hole by looking around it and seeing that emission, because we're not seeing anything directly emitted from the black hole itself in those images. So as we get to this accretion disk, and that's sort of where I see the outermost interesting feature. Beyond that, we're looking at matter that's coming into close orbit with the black hole. When you're talking about supermassive black holes at the centers of galaxies, you'll even have whole star systems in orbit around the black hole, but obviously much further away. And that's actually how we came to have the first sort of evidence of black holes is seeing the motion of whole star systems around the supermassive black holes in the centers of galaxies. So that's sort of how I see the structure as we move out. I'm obviously deliberately avoiding discussing inside the event horizon too much, because that's quite a hot topic of discussion, and one that no one can have much confidence in.
Yeah. I mean, I don't know if we'll even talk about that. I mean, obviously everybody wants to know, and yet there's almost no way to know. And so, at a certain point, it just becomes random speculation. But I think what's really interesting is, like, when we think about those images from the Event Horizon Telescope, we see that really cool orange structure that is around the black hole, and we see that it nicely matches the predictions made through general relativity. That's very satisfying. But in fact, there is this gap. And so, like, I guess it all just depends on the mass of the black hole, but just give a sense, like, say M87, we're looking at M87, and when we see that shadow of the black hole, how much closer is the photon ring to what we see in that picture?
It's a very good question. Yeah. I haven't got a fantastic answer for physical distances of how much closer it is.
Well, give me percentages, or some,
Yeah. I think the photon rings are extremely close to the event horizon, because, the gravitational force required to bend a photon is a photon traveling at the speed of light, obviously, is immense. So the photon rings are extremely close to the black hole itself, well within the accretion disk, and obviously very massively between black holes. I haven't got a great answer for
okay, but it's not
how it scales as we get close to the body.
Yeah, but I guess I'm trying to get at, like, practically speaking, and this is sort of where you're looking at, is what's it going to take to resolve the photon ring?
Sure.
And so you're looking at distances. You know that you're going to need something that can pick apart that gap between the accretion disk and the photon ring.
Yeah. Yeah, absolutely. So if we look at what the Event Horizon Telescope is capable of and what they've demonstrated so far, so they have achieved, the finest angular resolution that has ever been achieved in astronomical observations. Now, across all the wavelengths of light that we observe in any of our space telescopes, the EHT has achieved the finest resolution, and we're right down in the micro arc seconds of accuracy. And an arc second is a fraction of a degree. So you start looking at the numbers, and it's an incredible achievement in terms of resolution just to get that fairly blurry picture, which has become so famous. To begin to actually probe the structure of the photon rings, we're looking to go an order of magnitude better than that. So if the EHT was achieving 20 to 25 microarc seconds, we want to aim to get down as low as 1 microarc second, 2 microarc second, to really get us close to probing the second order ring. So that would be the sort of the limitation as we get down towards those levels of resolution.
I know there's they provide all of these sort of examples, because when you think micro arc second, or even just that whole process, right? Degrees, seconds, minutes, you are, it's like the angular resolution on the sky. And so there's things like, and I'm trying to remember, I don't know if this is I described it as a person on the International Space Station holding a half meter. Yeah. If you could see the astronaut on the International Space Station, then you would be able to see, pick out their body width from the ground. But maybe it's smaller than that. I forget the exact resolution of the Event Horizon Telescope. It's just ludicrous. But the point being, you're trying to go 10 times better, or is needed to go to see the photon ring.
Yeah, ideally that'd be what we need. I mean, just to give you an idea of the scale here. So the Hubble Space Telescope, for example, that operates at around a 0.05 arc second, so a 20th of a whole arc second, and we're talking about dividing an arc second into a million pieces, and observing with 20 millionths of an arc second. So right. To give a sense of the scale between these two systems, that's what's required to get these photos of these.
Right. And you want to see two millionths of an arc second.
The ideal scenario, if we could launch a space-based system, so I'm sure we'll get into this, is going an order of magnitude better than that.
Right. Okay. Yeah.
And you essentially have to go into space to do that. Yeah.
Right. And so let's talk about that. So because using interferometry, astronomers were able to build a telescope the size of planet Earth, and they were able to achieve that, say, 20 millarc second resolution. We're all out of planet. We can't make it any bigger. So how do we make our telescope bigger?
Sure. So resolution is dependent on only two things, essentially, and this goes for all telescopes. It's the wavelength you're observing at, and it's the physical size of your antenna, and that it's related to both of those things. So in terms of the wavelength, we can increase resolution by observing at shorter and shorter wavelengths. So we can do it that way. We can reduce our observational wavelength, and there's reasons why that's also difficult we can get into. Or we can make our telescope much, much bigger. And that's the driving force behind having massive telescopes on the Earth is that and sensitivity of the system. So obviously with VLBI, so very long baseline interferometry, which is the technique that the EHT uses, we have these antennae that are physically separated on the Earth, absolutely, thousands of kilometers apart on opposite sides of the Earth. So we have a telescope, a virtual telescope, that is the diameter of the entire Earth, and we can get into how this practically works if you'd like to. But obviously we are limited now because, like you said, the planet can't get any bigger. We can't get our antenna on the Earth any further apart. So from that point of view, the obvious benefit of going into space is we are no longer limited by that problem. We can put them as far apart as we absolutely want to. There become other issues with doing that, but in theory, we can put them as far apart as we want and get down to incredible levels of resolution. The other massive benefit is when you're observing within the Earth's atmosphere, we can go up to around 350 gigahertz of observational frequency. So getting down towards less than a millimeter wavelength, and the EHT is approaching this boundary. Above that, absorption of the waves in the atmosphere and distortion due to that makes observation above that impossible. But again, if we go into space, we haven't got this atmospheric problem anymore. So we've removed there's two big limitations on observing by having these systems in space. And then really, from a theoretical point of view, you have no limitation. It's more of your limitations then become technology and what we can practically do from an electrical point of view.
But I know, like, when you think about all the wavelengths, radio is the one that is most forgiving for observing from the surface of Earth. You can see through clouds, you can observe during the day. Like, the atmosphere isn't the same kind of issue as it is for other wavelengths. But for these kinds of observations, do you really feel like, practically speaking, you do want to get back to space, that the atmosphere isn't doing any favors?
Yeah, so I think radio is forgiving in that respect, you're right. And it's also forgiving, and the reason we use radio waves is the technique of interferometry requires very accurate synchronization of our measurements. And as we get down to really short wavelengths, shorter than radio, down towards even optical, visual light and X-ray, gamma and beyond, as we decrease the wavelength, we can't record the data with the stability that we need to. So that's the first reason we're stuck with radio for VLBI for the time being. But yeah, I think you absolutely do have to go into space. It's a physical limitation where we just there will be a physical limit on our resolution because of those two effects combining, the size of the Earth and our atmospheric problems. That just any technology, no technological developments could overcome that.
So let's talk about the baseline first. What kind of baseline do you think is going to be necessary to achieve that to milli-arc-second resolution?
Sure. Yeah. So it very much depends on the frequency that we observe at. But if we observe at something close to sort of the EHT's resolution, the EHT's frequency, we're looking at trying to achieve something of the order of like 100,000 kilometers. So we're greatly increasing the length of the baseline. So if the Earth's radius is around 6,300 kilometers, something like that, then we're going, at least 10 times bigger than that with our telescopes. And a key part of VLBI is to achieve a varied baseline. So the baseline is the distance between the two antennae, for those who are not familiar, and to get good coverage of our source during observations, we want to vary the length of that baseline as much as possible. So ideally, and an orbiting system allows us to do this. Throughout the observations, our two space telescopes, the distance between them will change over time as we complete the observation, because this allows us to sample a large range of sort of spatial scales and resolutions on the image, so we can get good resolution of big structures in the source and those really fine details that we want for things like the photon rings. So that's what we're really trying to achieve with a space-based system is that varied baseline, which again is difficult on the Earth because we're only the change in the baseline on the Earth is limited by the rotation rate of the Earth as well, again, which is something we cannot change. But now, once we're in space, we're moving at orbital velocity, kilometers a second, and then we've got this massive variation over short periods of time, which can be really, really beneficial.
That's interesting. So, like, when I think about the Very Large Array, they've got these giant radio telescopes in New Mexico that are on train tracks, and they're able to change the shape of the array depending on what kind of observation that they're trying to make. They want to bring them all tight in, or they can sort of spread it out to make a larger effective antenna. And I would sort of always think about the drifting in space to be a problem, especially with interferometry, because you want to keep those spacecraft. You want to know where your two spacecraft are in relative to each other, so that you can create your do your interference. But in this case, you're seeing it as an advantage because it gives you different perspectives. Is there a orbit that you're thinking of? So
I've been looking into the sort of practical orbit configurations we could use to do this work, and I've looked at a range of types of orbit, essentially, because there's obviously, when you select an orbit for a mission, there's more factors than just the science you're trying to achieve. That's from a physics point of view, that would be our only driving factor. But reality kicks in, and the spacecraft have to be able to operate in space, and there's a number of constraints this places on the orbit we can choose. So I've started looking at the kinds of orbits that would be feasible, with some technological development and some development in our space capabilities, these would be feasible. So I looked at some combinations of Earth orbits, so operating out at sort of geostationary altitudes and beyond, but at high inclinations. So there are a couple of configurations that work in that regime. And then just to get a nice sort of distinct change to that, which has and offer different advantages, disadvantages of the configuration. I've also looked at orbits around the Lagrange points. So we're very familiar with the James Webb Space Telescope out at the L2 the L2 point.
My audience is so familiar with Lagrange points, it would blow your mind.
Oh, yeah. That's good. That saves some discussion, so that's good.
Yeah. So, like, are you thinking like L4, like Earth Moon L4, L5?
So I've stuck with looking at L2 for the time being. L2 has a number of nice benefits for the same reason, basically, that James Webb picked it. We have a similar...
But Earth Sun L2.
Earth Sun L2, and I also looked at Earth Moon L2 to provide a nice variation on those two types as well, because that has a number of advantages that an Earth orbit configuration or an Earth Sun L2 position wouldn't have. Sun Earth L2 is interesting. Same reasons as James Webb. We have this constant sun position throughout observations, so we can use large sun shields, and we have a far more stable thermal environment for the spacecraft out at L2 than you would have in Earth orbit. And the same applies for a VLBI radio telescope. We're going to need to cool the receiver electronics on board down to incredibly low temperatures. And in fact, the higher frequency we go in observations, the shorter wavelength we use in observations, the colder the receiver will have to get. So there's a massive benefit from being that far away from the sun with a constant sun position. So you can use a sun shield to get that down. So that's pretty similar, James Webb's driver for being that far away, and a lot of other space telescopes at that position. But then we have other problems with VLBI, which James Webb does not have to the same extent. The amount of data we need to record during observations is absolutely massive. So the EHT, to give you a sense of how much data we're talking about, of course, terabytes of data every day. And I think it's a story that went around a lot during the release of the first image. They physically ship the data storage by post to the correlation center because it's just not feasible to send it over the internet. So that's how much data we're talking about, which is fine on the Earth because you can just we can just ship the memory storage across the Earth to the correlation center to process the data. But when we're in space, we've got to downlink that data via some sort of link to a ground station. So being miles away at L2 makes that incredibly difficult. The further away from the Earth we get, the much lower data rates we're going to achieve. So there are benefits in trying to achieve this varying baseline effect near the Earth if we can. And that's a sort of trade-off you have to make when you're designing spacecraft is get an understanding of how those things are going to affect things like the downlink rate and your power generation and your thermal control. So I've looked at a big range of orbit configurations essentially just to provide us with a number of options going forward as we're in the early phases of this sort of concept development.
And so you need a place that is at least 100,000 kilometers away from Earth. And so that rules out, say, geostationary orbit. But you don't want to be too far away because then it severely decreases your bandwidth home to send all this data back home. And I remember like the stories of them having to wait until winter in Antarctica was over so that they could put all the hard drives on the airplane and fly. Like they took the data, but nobody could look at it because they needed to wait another couple of months before they could actually fly the hard drives out with an airplane. And that limitation is gigantic. And people don't even realize, like when New Horizons went past Pluto, it took 18 months to get the data home because the bit rate was so slow. And so do you like right now, is it more about high bandwidth or is it more about longer baseline? Like where are you leaning?
I think if we're talking practically about the difficulties of implementing this kind of system, the data handling is the biggest problem. And there are a number of problems. Thermal control is one, but that is something we're quite used to with our telescopes. We've managed to cool down electronics on a range of systems to very low temperatures using like cryogenic techniques. So that's fairly manageable, I think, with, no doubt advanced equipment, but stuff we've done before. The data handling is something we haven't done to this extent in space before, not this level of data storage. And creation and building sort of radiation tolerant memory systems to store that data, again, very doable, but it is that downlink of that data back to Earth becomes very hard indeed, and something that we can't just overcome with technology development necessarily, because we are approaching physical limitations of what we can do with antennas. So I think there will be a desire to go as far away from the Earth as possible from a thermal point of view and from getting the biggest baseline you can. But the biggest restriction we're going to see is this ability to actually handle the data. But we have some ideas as to how we could cope with that problem going forward.
So I mean, like Earth, Moon, L1 gives you the distance and keeps you reasonably close, but requires a certain amount of, more heat blocking than being out at L2. That's interesting. It's right now you clearly don't have one solution that is screaming. Like obviously, like a million people are going to say the far side of the moon.
Yeah.
So what do you think about the far side of the moon as a choice?
The far side of the moon is a good choice, and that is one I have looked at. So like an Earth Moon L2 position. So still in orbit, but we're now.
But not on the surface.
Not on the surface. No, I'm still thinking about staying in orbit, because that does give us this rapid variation that I was talking about earlier with the baseline. There are some proposals though for radio telescopes on the far side of the moon, which are really interesting, which are worth people looking up. There's proposals for using craters on the far side of the moon for radio telescopes, which is an interesting idea. But yeah, if we look at the Earth Moon L2 point, it's still in orbit, but at that far side, we're sort of combining the benefits of those two other configurations. So we're combining the being sort of close to the Earth, but also far enough away so that the thermal effects of that become a bit more negligible. So it's a nice middle ground, and that's why I included it in my study. It sort of provides the benefits of both, and it is something that's a hot topic at the moment, because lots of the lunar missions are discussing going to very similar orbits that I proposed in my paper. So near it, linear.
And there's a need for a relay on the far side of the moon to communicate with lunar exploration. So
absolutely, yeah, it's an interesting idea with how many missions are going there. Whether it's maybe something could be made use of in a VLBI way that's already going to that position. That's an interesting concept. Yeah,
that's interesting. That it's not primarily like the Chinese Chuiqiao relay satellite did that. So they had a Dutch Astron experiment on board that was doing like submillimeter observations of the universe at the same time that the spacecraft was acting as a relay for Earth. And so it'd be interesting to sort of see if you can sort of partner up with that. So this leads then into the second part of really this question. We've talked about how big and where's a good place to put it. And the question is what is it? So what are you thinking is the right kind of machine? What kind of instrument do you expect it's going to be?
Sure. So we're talking about a fairly large radio telescope. So this is a big deployable antenna, so similar to the parabolic antennas you see on the ground, but we're talking about something of that nature. Another big problem of VLBI is sensitivity. So although we have this virtual telescope the size of the Earth or even bigger, obviously we don't really have a telescope that big. So we're not collecting data across such a large area. We've got this massive baseline, but only collecting over these tiny areas of antenna. So getting the antenna as big as we can is important as well. So ideally, and the sort of values I looked at in my work is a deployable antenna of 10 to 15 meters in diameter. So a large deployable, something we have done before to that size, but there are some interesting difficulties from an engineering perspective to building a telescope that large and keeping the surface accuracy high enough for sort of high frequency observations. So we're talking about a 10 to 15 meter deployable antenna system. Straight away we have a very large spacecraft because of that. We're talking about a pretty high level NASA or ESA, space agency proposal to do such a mission. Very likely a sun shield of some description. As I said, we need to cool down the receiver electronics to sometimes very close to absolute zero. So I think that'd be very difficult without a sun shield in any of the configurations I've just described. So you could picture a James Webb-like sun shield when imagining this concept, and instead of James Webb's nice gold mirrors, a big parabolic deployable antenna is what we'd be using for this. And then obviously the key thing for this mission is we're not talking about a single telescope, we're talking about at least two, which then increases the size, the scope of the project, the scope of the mission, the cost. But to do VLBI, we need at least two systems because that's, of course, the whole point. And the more, the better. Because you get
so you can't get by with just one and use the Earth as the other side of the baseline.
So you absolutely could do that. That is absolutely true. So, and missions have done already. So there has been a couple of VLBI space missions to date. Radio. You mentioned the Astron.
There was a Russian one,
Chinese.
right?
There was, yeah. So Radio Astron was on the Spectre R spacecraft,
right?
Sort of 2010 time, I think, and they were doing ground to space VLBI. So that's great for getting massive baseline, but you're still limited by that frequency that I mentioned by observing on the Earth. So you have to stick to that because obviously your ground stations can't observe any higher than that. So you can absolutely do that. We could launch a single telescope and observe in collaboration with EHT and other arrays, which has massive benefits because we've got huge number of telescopes now. But then you do have this limit on the frequency again. But actually, most of the sort of feasible concepts we're looking at the moment are aimed towards that kind of system, from the point of view of money, cost, and the fact that the EHT is already in operation. So, adding on to the EHT is a simpler idea.
Now, does the sun shield have to block the entire dish, or does it just have to block the electronics?
The receiver electronics are the key thing. So the antenna surface would have to be kept to some reasonable temperature. I haven't got a good number for that at the moment, but there would have to be some sort of control of the surface itself. But the receiver electronics need other thing that needs to be down close to, a few Kelvin if you're observing up at some of the really high frequencies that I've analysed.
So I'm just wondering whether you could have like a small sun shield that just keeps the core electronics, but then the rest of the dish is in sunlight, or are you going to have to deploy a sun shield that is big enough to protect the entire dish and all of the electronics? Because that's a taller order, right? Like I know with Webb, that sun shield was a headache of the highest order. And so to go, well, I like that, but now I need one that can be the size of a football pitch, not a tennis court. You're going to have a lot of engineers go, are you sure this is what you need?
Yeah, and absolutely. I think the general rule you can always assume with spacecraft engineers is we try and stop things moving as much as possible. So if something on board the spacecraft is going to have to move, it's only going to be there if it absolutely needs to be. So any deployables, anything like that, you're going to try and minimize those as much as possible because they are areas of high risk of failure, as we've seen on lots of missions before. And like you said, the complications with the James Webb Telescope and the moving parts, the complexity was incredible. But it's an interesting point, and one I think we need to do more analysis around as to the size of sun shield that would be required.
Is there a trade-off, right? Like, is there a trade-off for like just a bigger antenna? Like if you like no sun shield, but it's a 20 meter antenna, no sun shield, but it's a 40 meter antenna. Like I wonder, does that get you back to what you need without having to keep the whole, or is there just enough cooling very specific parts of the telescope?
Yeah, that's a good question. I think the limiting problem would be the frequency you want to observe at. So if you're happy for your receiver and other electronics to be a higher temperature, then you're just going to limit how high a frequency you can observe at. So it will come down that way. So there's absolutely a trade-off there. And as you said, you can increase antenna diameter and make up some of the difference that way as well. But there's certainly more thermal analysis required to properly determine what a mission like this would need. And I think it's an interesting part of this because most people working on these concepts are physicists. And obviously that is absolutely necessary from the scientific point of view, but there is certainly this jump to then reality of what we can feasibly achieve with such missions from an engineering perspective that you need to make. And I think we're in the process, with the groups I work with, we're in the process of making that jump to, okay, how do we really do this now? What do we really need to be able to develop over the next 5 to 10 years to make this feasible? So that I think that realization is currently dawning, and those discussions are starting to be had.
I mean, there's some really interesting technologies being developed in 3D printing where people are proposing building struts and structural elements and even radio dishes, in place. Like, have you looked into any of that at all?
Yeah, it's a good question. I haven't looked into 3D printing in orbit as of yet, but what I have been considering is the fact that obviously a hot topic, SpaceX's Starship, some of the capabilities that's going to provide us for transfer of mass to Earth orbit and beyond, and also the size of payload that the Starship can transport, and that's going to take us well beyond sort of the fairing sizes we've previously seen on our launch vehicles. So from the point of view of a deployable structure that originally would have been limited by the size of the fairing, or that would be one of the limitations. I can see how we can begin to move beyond those limitations with something like Starship, where we have these potentially massive deployable structures because of the large fairing size. So I think that's a really interesting thing to consider, and I think it's something that will dawn on people more as obviously their launches become more frequent and more successful.
I mean, I think the thing that's really great about radio is that it is more forgiving. So you don't need to reach the kinds of tolerances with your dish that they had with James Webb.
No, true.
And so if you're going to try to build things in space, assemble them in space, unfold them in space, you don't have to be as careful as they had to be with Webb.
Yeah, that's absolutely true. And although we do need a certain level of accuracy in our deployable, it is not of that order. You're right. Deployable structures are, as Webb's shown, particularly parabolic antennas to deploy, are tricky to deploy to the accuracy you need for these higher frequency observations. So that is one challenge that a lot of groups are currently looking into, is what can we feasibly do right now with our antenna manufacturer for a deployable system. There's an alternative to that. In fact, we could use almost a phased array system, so where you essentially have a number of antennas on the same spacecraft rather than one single parabolic dish, and then the accuracy of their positioning is not so key, because you could actually tune their and calibrate their contributions to a single receiver by performing calibration exercises. So that's one thing that's being considered to get around the antenna manufacture problem. But you're right, we're not down at the level required for the James Webb deployment, which is again why one of the reasons we do use radio waves for this.
I mean, one of the long-term goals is a space-based interferometer, and the only practical one that's in motion right now is LISA, which is going to be doing gravitational waves, and they're back to requiring incredibly tight tolerances. And when you look at the timelines on LISA, it's like 2035. Although it's getting surprisingly quick when I think about how long we've been watching this mission. It's only 12 years away now. But it feels like the place to begin learning to run an interferometer is with the most forgiving wavelength, and that's radio.
Yes. Yeah, absolutely. And it's the key challenge of VLBI, which does force us into this radio world. Like I said, when our two antennas are observing the source, we need to synchronize the recording of those signals as accurately as you possibly can. So on the ground, the EHT, each station has an atomic clock. So that's required. So on board the spacecraft, you would almost certainly need an atomic clock. So that's again another level of complexity that most space telescopes don't have. So that atomic clock is required to get that stability of the sampling of the signal. And then in addition to that, we need to synchronize the measurements between those two telescopes. And the EHT uses GPS to do that, which provides a very stable pulse from which they can both synchronize their clocks during observations. This is why we use radio, is if we were going to higher frequencies, shorter wavelengths, to get that stability of measurement and synchronize the measurements such that you could correlate the data and get anything useful out of it once you've completed your observation. We're not at a point where we can do that with wavelengths shorter than radio waves. So that's why VLBI inherently uses radio. It's a limitation of technology, essentially, and a limitation of timing that we can achieve. But all these things I've described on the ground are things that we need to somehow find solutions for if we want a space-based system as well. So this is where the biggest challenges come, is trying to translate the things the EHT does to a space-based, maybe one or two spacecraft, but you have to try and overcome these problems that the EHT has fairly drastic solutions to.
Right, but at least you don't have to try and figure out real-time interferometry the way any other wavelength would have to do it. At least get to have an atomic clock. Each telescope records its own version, and then you just send it later and let a computer mash it together.
Yeah.
You can't do that with any other wavelength.
No, that's true. And our challenge then becomes, how can we make that correlation process easier? Because it's a highly computationally expensive process and takes an awful long period of time, incredibly powerful computers to do that. And that's been the limitation of VLBI for a long time, is actual processing power. So we don't have that limitation, you're right, but we have the limitation of actually sampling our data in such a way that we can actually correlate it in the end. And this is a problem that past space missions have had. So Radio Astron that we discussed, they collect loads of data, they can record lots of data, but and get it back, and they got it back to the Earth okay as well. When they actually come to correlate that data, and find what we call fringes. So essentially lining up the waves from our different antennas so we get this interference pattern that we can use. That's incredibly difficult because you're searching in a range of sort of parameter spaces to try and find that detection. So it's not only time, you're trying to find the exact time that both antennae observe the same signal. You're also trying to figure out in space where they were when they received that signal as well. So you're searching across all these parameters to find that interference pattern. And the EHT does this, took a long period of time. It takes weeks to correlate data. We have to try and make that process practical and short with a space-based system, and that imposes most of the requirements we have on technology and the things that the space-based telescopes will have to do. So that's our difficulty compared to the other interferometers is the wealth of data and the correlation.
Is there like a hybrid approach? Like, is there a way to keep the thinking on the spacecraft as opposed to having to bring it home?
Yeah, it's an interesting idea, and one we've started to think about. So in-orbit correlation would be an amazing thing. If we could keep all the data up there, we remove our problem of getting it back down to Earth.
Just send the picture, send the pretty picture.
Yeah,
right?
Exactly. Ideally, just send the picture down. Send the graph down we want to analyze to get our photon ring measurements or whatever. We have again challenges. It would involve flying computational power that we haven't ever flown before. It would involve the two telescopes having to send the data between themselves, or one sending the data to the other. So at some point we still need to transfer the data to one of the other telescopes. So you can think about using an optical, like a laser in satellite link, something like that. Perhaps at some day that would be feasible. It's definitely a fascinating idea, because if you correlate on board, you massively reduce the data that's to come down to the Earth. So you can imagine being much further away from the Earth, using an intersatellite link, and then just sending down the much smaller final products that we want to see, rather than the full data set, which most of it will be discarded because we're searching for this, and we're searching for these interferences in massive amounts of data. But that's an interesting idea.
Yeah. I mean, it's interesting. Like, you look at, for example, like the Vera Rubin telescope, they're going to be processing so much of the sky that they're going to be doing a lot of the first analysis just in real time. They're just going to, as things are blasting through the pipeline, they're going to be pulling interesting scientific nuggets out of it and saying, oh, we found a supernova. Oh, we found an asteroid. Someone may want to look at this. And you can see there's this tension and this balance between, do we bring everything home, or do we figure out a way to get these telescopes to do some of the hard work remotely so that you can just send the results home, and then you're less bandwidth constrained, and now you can put interesting telescopes much farther away from Earth to do more interesting tasks. And at the end of the day, all we want are the science results. We don't, but now you've got to fly a cluster of NVIDIA H100s on your spacecraft, and I'm not sure they're space hardened yet. No,
exactly. Yeah. And again, going back to data rate and, often the boring side of things, but the realities of what you need to be able to achieve, the data rate you need to get on a laser and satellite link to transfer that much data to the other satellite would be immense. So whether you can do it in real time, or you can do it, after observation and do it slowly, that's probably more realistic. But again, keeping it all in orbit and then downloading the the data product later, that would be beneficial. And that's probably like a stretch goal, a dream goal for a system like this. There's definitely a few levels of complexity before that are more achievable in the short term.
Now, we've been talking about the Event Horizon Telescope, but the big telescope that's coming online shortly is the Square Kilometre Array in Australia and South Africa. Would you be in the same wavelength regime as that telescope and be able to work together with it?
That's a good question. Because as far as I'm aware, the SKA is not part of the EHT array as of yet. So I don't know.
Just like on the wrong side of the Earth?
Yeah, I wonder whether
is it nighttime when?
Is it like you said, a positional problem or a frequency problem? I'll have to look into the frequency the SKA is observing at.
I mean, I know that the two sites are slightly different chosen wavelength regimes, but I wonder if that's off from what the EHT is doing.
Yeah, I feel like it probably is, just for the fact that they're not currently involved in the next generation EHT, the current EHT. But perhaps it's something that we looked into in the future, because the contribution of such a large collecting area, essentially, is what the EHT wants from ground telescopes now, is getting larger and larger, because it's a sensitivity problem I discussed before. Is we need to collect over a massive area to increases sensitivity of our detections. So I wonder where that will go in the future. Perhaps that will be a future addition to the HT.
What could we learn from getting that image of the photon ring?
So this is a good question, because I've had lots of friends who, obviously I very excitedly showed this picture around when it was first produced, and it was amazing to me and amazing to lots of other people as well. But a lot of other people say it's a blurry photograph. As cool as it is, it's a fairly blurry photograph. But the science that can be done with even that EHT image is immense. So the first thing that they managed to do is they can use the generated image and compare that to a range of models we have on the Earth, and from that, in almost a comparison way, to infer a lot of characteristics of the black hole. So they came up with a much more accurate mass estimation of the M87 star black hole than we've ever had before, and one that was independent of other measurements, like auxiliary measurements that were required when those first mass estimations were made. So that's one interesting piece of information we can gather from that first image. And the other is just general tests of general relativity, so consistency tests of general relativity. So there is still some debate as to whether general relativity holds up in the extreme gravitational environment around a black hole, and whether that's still a useful metric to describe the behavior of matter around a black hole. And the EHT image and things we're going to try and get in the future will allow tests of that nature to be conducted, and they have done some already with the EHT image, and understanding gravity in that strong gravity environment is just essential to our overall understanding of how gravity works, which is a massive question in physics, and one that is particularly fascinating for black holes, because obviously we have this everyone knows this gap we have between the quantum mechanics world of physics and the general relativity, and they're trying to merge those two regions, and black holes are really where those two things come into, those two worlds collide, with the singularity at the center and the huge gravitational environment. So learning anything we can about gravity is the major aim of getting these photos, and there are wider applications. If we can understand why the mass of black holes are what they are, we can come to lots of conclusions about how galaxies form. So the supermassive black holes we've been observing so far, so it's M87 star and Sagittarius A star. These are two supermassive black holes that have the largest size when we view them from the Earth. They're essentially our biggest targets, hence why we go for them. It's as simple as that. They are both at the center of their respective galaxies. Sagittarius A star is the center of our own galaxy. It's our own supermassive black hole. And the question as to how they get there, or why galaxies form around them, is completely, is unknown, and something that still needs resolving. So the implications of just that image are a lot wider than just understanding black holes. It's understanding how the whole structure of galaxies form. And probing the photon rings does provide us even more than what the EHT can currently do.
So it's 20 years from now. The twin space-based event horizon telescopes are flying in space. Maybe they're at the L2 point, maybe they're at the L4, L5 point, and they have been recording their images, and astronomers have crunched the data, and they've got the picture. They've got the version, the photon ring telescope. When we're looking at the picture, what would we be seeing?
Yeah, so if we could image with enough resolution and enough coverage of the source to actually generate an image where we had the photon rings, then we would see the accretion disk in far more detail. We would see the matter going into the accretion disk. There's some fantastic simulations that people can see in papers where we can see the spirals of the matter going into the accretion disk, and we would begin to see the rings forming within that. And the power of that, if we could probe the first and second order rings, and even further, if you're talking about a dream telescope, by probing the EHT can't currently probe the rings. If we could probe the photon rings, we can do what I've just said before. So general relativity tests, mass estimations, but to a whole other degree compared to what the EHT can perform. So the interesting thing about the photon rings is, whereas the EHT is looking at the accretion disk, as I said before, so that below is the accretion disk, that's massively dependent on the sort of physical processes within the disk, and less so, well, not less so, but it's massively influenced by that, and therefore any measurements we want to make of the sort of gravity effect is corrupted by that interaction. The photon rings, the higher order you go, the less they're influenced by all the friction and the heat and the energy in that accretion disk. They're more dependent just on the gravitational properties of the field. So if we get those really high photon ring orders, we could detect those and probe those rings and estimate their diameters and all sorts of characteristics about them. We can have these completely independent tests of general relativity that aren't corrupted in the same way as the EHT ones are. And that would allow us to verify the kinds of black hole we're observing, which parts of general relativity hold up in these fields, and what kind of black holes feasibly occur in the real universe. And then if we're talking about having unbelievable resolution, we're finally going beyond just M87 star and Sagittarius A star. We can now look at all the other black holes.
Right. Well, that was my next question, right? Was that you, like, only these two black holes are within the limits of what we can see. And all of the others are too small, too dim, too far. But suddenly, so how many do you get? Like, if this comes online, how many just Event Horizon Telescope pictures can you take?
Yes, good question. So the black holes are surprisingly common in the universe. Despite Einstein's initial reticence at them even existing, our estimations now are closer to something like 10 million to a billion of them existing in the Milky Way alone. Small black holes, which we think can form when something of the mass, maybe 2 to 3 times the mass of our sun, dies at the end of its life, collapses at the end of its life. Now, supermassive black holes are another thing altogether. Supermassive black holes, we're looking at masses of around 0.1 million to 10 billion times more massive than our sun. So these are an entirely different animal, so to speak. And yeah, like I said, the reason we look at M87 star and Sagittarius A star is they're either so massive that they're big when we look at them, or they're much closer. So Sagittarius A star is not very big compared to M87, but it's much closer to us because it's in our galaxy. M87 star is an absolute monster. So it's about 6 billion times more massive than our sun. So even though it's in another galaxy, it's just so massive we can see it. Yeah, they both have a horizon on the same scale of resolution that we can achieve with the HT currently. If we can go an order of magnitude lower than that, I don't know if anyone's done this work as of yet as to what survey of black holes can we perform with different resolutions. It might be an interesting piece of work, but I imagine it jumps hugely.
Hundreds, thousands of black holes.
Yeah, and it's not even just a case of getting the event horizon. It's further away from a black hole, and the way we first saw them was seeing these big jets that the black holes produce. These massive spikes of magnetic field and energy getting erupted into space. So even if we couldn't get as close as the black hole in our images, just seeing that jet has massive implications in terms of the science you can do on that.
So cool. Ben, what are you obsessed with right now?
What am I obsessed with? So I'm a spacecraft systems engineer. So I'm not a physicist. I design and build satellites. That's my work. I'm in the practical world of this topic. But I'm obsessed with getting one of these systems accepted by a large space agency or by someone, getting it launched and actually operating that. Whether it's in conjunction with the HT or it's an actual purely space-based system. I'd love to see, in the next 10, 20 years, or perhaps even shorter timescale if we're lucky, a high resolution image of one of these black holes. I think that would be fantastic. I think just the effect that had on the general population, the interest that sparked that picture. I think black holes get everyone's attention eventually. Everyone realizes, oh, that's very interesting. And I think just increasing that clarity of that image, you'd get more and more people engaged in the topic. So for me, that's a big goal. I'd love to see those images get more and more fine detail as time goes on.
I can't wait to see that first picture from space.
Yeah, incredible.
Yeah. I mean, like a radio space telescope. Yes, please.
Yeah.
Yeah. Ben, thank you so much.
Thank you.
I'm going to give you some concluding thoughts in a second, as well as some resources that you can check out some more stuff. But first, I'd like to thank our patrons. A special thanks to David Richards, Mark Anstis, Antonio Lofilara, Dustin Cable, Vlad Shiplin, George, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. We really went into the details about what it's going to take to put a spacecraft that can form part of the Event Horizon Telescope. And it really shows you the different trade-offs that engineers have to think about when they're forming these space mission concepts. It's not just about how big of a telescope, it's where do you put it? And how do you unfold it? And how do you get it into position? And what are the environmental issues that you have to think about for different places in space? And then getting the data home. You want your spacecraft close to home, but you want them far enough away that they can do their job. And there's all of these trade-offs that are involved that make this so complicated, especially when you're thinking about something that's going to be having to record and transmit an enormous amount of data. And I kind of don't envy Ben for all of the trade-offs and all of the variables that he's going to have to account for. And yet, interferometers, like I just keep coming back to this theme. We need a space-based interferometer to take astronomy to the next level. And it makes a lot of sense, to go to the wavelengths of light that are most forgiving. And so for me, it really feels like it makes a lot of sense to both test out a radio interferometer in space, as well as starting to put more intelligence, more compute power onto the telescope, the mission itself, to be able to offload a lot of that difficult work where it's being needed and then send the results home. So there's like a lot of interesting technical risk challenges and milestones that can be overcome by taking on a mission like this. Now, if you want to follow this thought process a little further, I've got a couple of other videos that I've done. So one is talking about building a far infrared space interferometer. And then another interview that I did about building a giant space interferometer and some of the other values that you can get from that. So I'm obsessed about space interferometers. I hope you are too. And so there's more videos you can check out. All right, we'll see you next time.